Okay, so we can have some example here to look at which one is faster, current or voltage sensing. So, any guess? Before look at those numbers there. Any guess which one is faster? Of course, depends on those parameters, those two equations, right? So it depends on what is the number for those RB, RT, RC. But in this example, if we take a very old S-gram paper, I think. So then, for example, memory cell like 2.5 kilo ohm, and the total wire like 250 ohm. So it's a non-wire, so you have this wire resistance. And this is a very old technology, so the distance is none, and then the capacitance is like 2 pico. So you can plug in those numbers into the equation, because if you look at those equation here, only 3 parameters. So you can plug in the numbers. I will skip that. If you do that, you will get those 2 numbers. The voltage mode is like 5 nanoseconds, and the current mode is like 0.2 nanoseconds. So this is in this example with those parameters. Okay. So and here you see that voltage current mode is faster.
If we look at the equations, current mode is always faster because the factor that it's multiplied by is always less than 1, whereas this one has 1 plus something. So shouldn't it always be faster?
In this simplified
yeah.
picture, yes, you are right. In this simplified picture, yes, it's always faster. So, okay, so this is the bitline model, and then let's look at sense-amp. And let's look at some examples of the sense-amp. Let's say voltage mode first. So voltage mode, and very simple. Okay. So for example, for this SRAM, you will have the bitline bar, and then you will take the differential voltage difference into the sense-amp, and you can just design a very simple differential amplifier as this sense-amp. For example, here, this is the simplest differential amplifier. So you have the 2-bit line where you get those voltage, bitline voltage or bitline bar voltage, as input to the differential pair of this one. And then this is current mirror, PMOS as current mirror node, and then you convert the differential input to a single-ended output from this node, and later you can further followed by an inverter to clean up the signal to drive this out. So this is a very simple design. So I hope that this simple circuit you can understand this if you take any undergrad level analog circuit. So to improve this design, typically you want the speed, okay? Then this one is not the fastest. So if you want to improve the speed, you better use the latch as the node. This is exactly what we showed before in the SRAM or in the DRAM lectures. So what you can do here is to have the latch, and then you pre-charge those two nodes, and then this latch initially is in the metastable point. Actually, this should not be the voltage mode. I should not say this is voltage mode. This latch-based. Actually, it's more like current mode to me. So this guy, you have those two nodes, and before the sense sample enable signal, those two are in the metastable point. But then later you will enable the sense sample enable signal here. Then depending on the difference between those two, then the snatch will flip. Because the latch, due to the positive feedback, the flip is very fast. So you can improve the speed in this case.
Sorry, Professor, that's not a voltage sense amplifier. It's just just a simple latch-based.
It's a simple latch-based, yeah. But you can use this latch-based one to improve this guy. So what you can do here is to replace this part with a latch. So basically those two nodes can be those two nodes. So still here you have the voltage input through the differential pair here, and then this differential pair, then the pull down strength for those two nodes will be different. But this latch-based one will flip faster than this one, this current mirror one, because it's positive feedback built in the latch. So if you have any voltage difference here, then it will quickly flip. And then this is current mode. So this is just one example for the current mode. Here this is your memory cell, so you have current in. Still you have the differential input, and here the load is like a latch, this positive feedback circuit. So here those 4 transistors here is like a latch. But here the current is into here, and it's like the current goes to the source in this case for the M1 and M2. So why is this current mode? Any idea? Why is this like a current mode? So we discussed that voltage mode, you want what? You want the input resistance of your sense amp to be very large. Current mode, you want the input resistance very small. So if your signal is to, let's say, the gate of the transistor, it's a voltage mode, right? Because gate should be like open circuit from the if you look into that. So you have the voltage on your gate. But if your input is to the source of the transistor, you flow current into the source. And if you recall the analog circuit design, what is the input resistance if you look into the source of the transistor? What's the value? 1 over GM. Yes. So if you recall your analog circuit, of course this is a not small AC signal with a sinusoidal wave, but still it's a small kind of small signal. It's not repeated like the sinusoidal wave, but still it's like a small current into that. You can use that concept, like the input resistance very small from the source side to the transistor. So that's why this is like the current mode. So still depends on those two currents, input current, then those two voltage in this latch will be different. And then once you enable this latch by this sense amp enable signal, then those two will flip. So remember, for any latch-based sensing, you need to have this enable signal, right? So basically you need to make the latch in the meta-stable point without turning on the sense amp enable. Because sense amp enable essentially will collect your latch either to the VDD or ground. So before you turn on the sensor enable, it's okay because the circuit is floating. So those 2 points of the latch will be the equal potential. But once you develop the difference of those 2 nodes, then you turn on the sensor enable. Then you have a path to the VDD or ground. Then this latch will flip. Okay. So here, I think this paper is a nice paper to summarize some of the advanced techniques for the voltage mode and current mode sensor design. And here for the left one, this is like a voltage mode sensor for the R1, 1T1R structure. So essentially you have the 1T1R here, and then this will pull down the bit line voltage depending on the resistance value. If resistance value is large, then the current is small, so you will pull down this node slower. So essentially this can be divided into a few steps. First one is pre-charge the bit line. You pre-charge this bit line to be a high value. So your bit line start with some high value. And then after you pre-charge, then you turn off the pre-charge. Now you turn on the word line in this case. So then, depending on the resistance here, then the current can be large or can be small. If current is large, then you are going to decay this node faster. If current is small, you will decay this node slower. So you need to wait for some time to develop the bit line voltage. So essentially you want to open this window between those 2 states. If you are sensing on and off state, then the decay speed will be different. Then after you wait some time, then you have a voltage difference between those 2 states. So then the other side of your input will have the reference voltage somewhere in the middle. Then you turn on the sensor enable because you already built the voltage difference here between the bit line voltage and your reference voltage. Then you can turn on the sensor enable. In this case, it's a latch. Then you can flip the state. So you need the 3 steps here. And the right one is the current mode sensor, still for this 1T1R cell. And this design is that you will have a current mirror to mirror this current to here, and this current is going to send to the drain of those 2 transistors here, which will the drain to those 2 transistors, but will be the source for those 2 will be the drain to this 2 transistors. Still, depending on the current difference here, the load voltage of those 2 will be different. And then you can use an inverter to amplify that signal. So this is a current mode. And you can read the details from this paper. So in this paper, I think they did a comparison between those voltage mode and current mode through the real spice simulation instead of what we discussed earlier using the simple bit line RC model, right? So this one is to really run the spice simulation of those 2 circuits we showed in the previous slide with different conditions. So the conditions will change. First is the array size, or let's say the number of cells along the bit line. What is your number of cells along the bit line, or how many rows in the subarray? And the second parameter here is low resistance state. What is the resistance for your memory cell? Let's say 10 kilo ohm or 100 kilo ohm. So here you see the result. This is latency, access time. So if the resistance is small here, for example 10 kilo ohm, which is this triangle symbol, so you see those two curves here. Of course, with larger array size, then the access time will increase. And you see that if the array is very large, then this red one, which is current mode, will be smaller in the access time. That means faster. So you see current CSA current is faster for this large array. But voltage mode may be faster for small array. And then if you increase the resistance to 100 kilo ohm, then the turning point will shift from here to here. So now if it's 100 kilo ohm, then let's say if you are larger than 128, then the current mode is faster. So you can do this comparison by the SPICE simulations. And in general, for large array, current mode is faster. And here, the challenge for the sensing is that if you want to sense small current, that means large resistance is challenging. So here we show this trade-off: access time, read speed, and the cell current for the memory cell. So here we see the difference between NAND and NOR we discussed before. So NOR is, this is flash, okay? NOR flash is fast, like tenths of nanosecond. The reason is that the NOR flash single floating gate transistor attached to the bit line, and that current from that NOR flash transistor can be tens of microamp. So you can sense that within like tens of nanosecond. But for the NAND flash, you go through that string of transistor, then the current is very small, like typically hundreds of nanoamp. So that's why you need this tens of microseconds. This is like 10 microseconds, tens of microseconds to sense. So this is the trade-off. And basically this paper proposed some schemes to push the sensing possible here. Even you sense like hundreds nanoamp, but still you can sense it within like tens of nanosecond. So if you are interested, you can read this paper. So through very dedicated scheme to improve the speed, it's possible. However, the overhead is that you need more transistor or some switch cap or cap capacitance there to sense this. The area is not small if you want to do this. So any questions? I would say for a memory design, the most challenging part is the sense amp design. So it's I'm not an expert in that, but this is really the, I think, the core. I mean the or let's say frontier of the research for memory array design is on this sense amp. There are many new designs coming out to address the challenges, such as we discussed the small current, and also another thing we didn't discuss is the process variation. So that will lead to the sense amp offset. So how do you compensate the process variation? Okay, so let's move to the next topic, which is the higher level organization. So here we are going to introduce this bank model used in this simulator, which you are going to use for the homework 5. And here this is one bank in the model, and I think this uses the terminology from the DRAM. So the high level is a bank, and then one level below is a mat, and then one mat may have multiple sub-array. So then you can have this kind of hierarchy. So the question for the high-level design is, how do you size each mat or sub-array? So let's say you have a total capacity of the memory. How do you design the size of each mat or sub-array, or how many sub-array, let's say, become one mat? So those are the design questions from the system's perspective. So for example, those are two possible designs here. The total number of memory cells are the same, but you can have less number of sub-arrays, but each sub-array is larger, or you can have more number of sub-arrays, each is smaller. So which one do you prefer? Any idea?
Depends on the application.
Yeah, depends on the application. That's the correct answer. So if it's for cache, which one do you prefer? Left or right?
Right.
Right. Yes. So if you care about the speed, then you want to break up into smaller subarray, because the distance for the wires shorter, so RC delay shorter, so then faster. But of course, it's less area efficient because each subarray will be equipped with those peripheral circuits, like decoder, sensor amp, and so on. So the area efficiency will be lower. So this is exactly you see in the SRAM cache. Let's say on the right hand side is a SRAM cache. Left one maybe a DRAM, right? So the DRAM you can sacrifice the latency a little bit, but you care about the density, area efficiency. So you want to make this larger. So those are the design choices you may have to take. So in this model, it considers not only how many rows, not only how many subarrays in one mat or how many mat in one bank, but also it considers how many of them are active during the access. So you can access the data from multiple mats simultaneously. So here it says those parameters says the activated mat per row or per column in this bank. So if 2 and 2, that means you can access those 4 mats simultaneously. So those are the design questions for the high-level system architect to decide. And also for the routing from the higher level point of view, you just think about how you get the data from each subarray. So you typically there's a routing called H tree. So it's every, let's say, intersection here is 2 branch. So you go left or go right, and then go to here, you go up and go down, and then again left and right. So this is a typical routing scheme. So those routing basically are wires with buffers. So because when you travel long distance, you need to use buffer or repeater to recover the signal, digital signal. So this is a typical way you get those individual bits from subarray and then combine them and then go to the external I/O. So here are different schemes to do this. You can have sense amp placed locally at the end of each subarray. So that means after sense amp, your signal will be digital, and then just send the digital signals along the H tree through the repeater or buffer and to the outside. So it's like a data bus. And this is a full swing signal. That means digital 1, 0, or VDD to ground kind of signal. So you get the. But if you want to improve the area efficiency, if you don't need so many bits simultaneously, you can share the sense amp outside the mat. So multiple subarray share the sense amp. So if you do that, then you are going to share the sense amp, multiple subarray. Then in this wire from the subarray, actually you are using the partial swing signal. That means those are still analog signal, like delta V, a small signal. Because before you go to sense amp, sense amp is to convert analog to digital, right? So before you go to sense amp, the wires carry the partial swing signal. And then after the sense amp, you convert to the digital. So in this case, you have to carry the partial swing signal, and you may care about the noise in this case. But the good thing is that you save the area, because your let's say I/O does not need so many bits anyway. So you can have different design options like this.